Let's turn our attention now to limits as x approaches infinity using algebra. So we have this basic rule here. It says for k greater than 0, in other words, k is a positive number, the limit as x approaches infinity of 1 over x to the k power is equal to 0, and the limit as x approaches negative infinity of 1 over x to the k is equal to 0 as well. So recall that we said that as x approaches infinity or x approaches negative infinity, that is all talking about the end behavior. And so if I look at these graphs, and what I'm going to do here is I'm just going to pick some samples. It's not really a proof of this idea, but hopefully it'll give you enough perspective on how this works. So suppose I have the graph of y equals 1 over x. Well, we know that it looks like this. And so as I take the limit as x approaches negative infinity, it gets closer and closer to 0. And the limit as x approaches positive infinity, it gets closer and closer to 0 as well. So that works on both sides there. Well then, what about y is equal to 1 over x squared? Well, 1 over x squared looks something like this. And so still, as x goes to negative infinity, it gets closer to 0. X goes to positive infinity, gets closer to 0 as well. So basically what's happening is that the x's, let's say that as the x's go to infinity, then x to the k power goes to infinity as well. And then as something gets larger by going to infinity, what happens to the value of the reciprocal of that? So think about it this way. Let's say that the value of x to the k, as we're trying to go to infinity, and we'll just make a little string of these. And so suppose that that value is 1,000,000, and then 1,000,000,000, and then 1,000,000,000,000, and it just keeps getting larger. Well then, what is the value of the reciprocals of those? Well, it would be 1,000,000th, and then 1,000,000,000th, and then 1,000,000,000,000th, and then smaller and smaller and smaller until it gets closer and closer to 0. And so that's where these rules come from. If you have the limit as x goes to infinity of 1 over x to the k, then it gets closer and closer to 0. And it works the same way on the other side. It's getting closer and closer to 0 as well. Example number 9. Find the limit as x goes to infinity of 4 over x cubed. Well, there's a rule that says if you have a multiplier number, like this 4 here, you can actually bring it out to the front and multiply it by the value of the limit. So I'm going to pull that 4 out, and this is going to be 4 times the limit as x goes to infinity of 1 over x cubed. And now this piece can, we can apply my new rule here, it's in the box above, that says the limit as x goes to infinity of 1 over x to the k goes to 0. Well, the k here is 3. So this is actually equal to 4 times 0, and that's equal to 0. So this limit is 0. So multiplying it by 4 really didn't do much. Let's take a look at the procedure for determining limits at infinity. So this is both the limit as x goes to positive infinity or the limit as x goes to negative infinity. This process works for both of those. First, you want to divide each term in the numerator and denominator by the highest power term x to the k from the denominator. It's not the highest power term anywhere. It has to specifically be one from the denominator. Then you're going to simplify each of those terms, and then you'll take the limit of each of those terms, knowing that the limit as x goes to infinity or negative infinity of 1 over x to the k, where k is positive, is equal to 0. So that's going to make most of the terms go to 0, maybe not all of them, and we'll handle those extra cases as they come up. Example number 10. Find the limit as x goes to infinity of 4x squared minus 3x plus 2 divided by 5 plus 6x minus x squared. So we are going to divide by, and then let's look for the highest power term in the denominator. Well, it's going to be x squared. You can ignore the negative and any of the coefficients that go along with that highest power term. They're not relevant. So the limit as x goes to infinity of 4x squared minus 3x plus 2 divided by 5 plus 6x minus x squared. This is going to be equal to the limit as x goes to infinity of 4x squared divided by x squared minus 3x over x squared plus 2 divided by x squared. This would be a really big one here. 5 divided by x squared plus 6x divided by x squared minus x squared over x squared. Now, we might want to ask, why can we do this? And the answer is because you're technically dividing or multiplying, however you want to think about it, by 1. Because I'm not doing it in just one part of the fraction, I'm doing it in both parts of the fraction. So in essence, I'm dividing by x squared in both the numerator and the denominator, which is a factor of 1. So it doesn't change the problem at all. So we still have the limit as x goes to infinity. Now I'm going to simplify each of these. So this is going to be 4x squared over x squared is just 4. 3x over x squared is 3 over x. And plus 2 over x squared, nothing cancels there. 5 over x squared, nothing cancels here. 6x over x squared is 6 over x. And then x squared over x squared is 1. And now I can take the limit of each of these individual terms. So the limit as x goes to infinity of the number 4 is still just the number 4. There are no x's to affect the value of that part of the function. It's 4, it's always 4, and it always stays 4. The limit as x goes to infinity of 3 over x is 0, because it's technically 1 over x times 3, which we've solved before, turns into a 0. 2, the limit of x, as x goes to infinity of 2 over x squared, that's a 0. And then 5 over x squared is going to go to 0. 6 over x goes to 0. And negative 1 stays the same. So that's negative 4. And that's the limit. Now don't lose sight about what this quantity actually means. This is the end behavior of the function. And that function is that 4x squared minus 3x plus 2 over 5 plus 6x minus x squared. What that tells us is that as the x's get larger and larger, and you start graphing things to the right side of the graph, they level off at negative 4, and that creates a horizontal asymptote. At y equals negative 4. Example number 11. Find the limit as x goes to negative infinity of 6x squared plus 13x minus 49 over 7x plus 9. So we again look for the highest power term in the denominator. It's just x to the first. So we're going to divide by x. We ignore the 7. So write out the problem. Limit as x goes to negative infinity of 6x squared plus 13x minus 49 over 7x plus 9. This is going to be the limit as x goes to negative infinity of 6x squared over x plus 13x over x minus 49 over x all over 7x over x plus 9 over x. And then we simplify. 6x over x is still 6x. 13x over x is 13. Negative 49 over x stays the same. 7x over x is 7. And then 9 over x. And now we attempt to take the limit of each of these. Now this term here is going to go to 0, this 49 over x, and the 9 over x is going to go to 0 as well. The 13 is fine, the 7 is fine, but this 6x right here, that's a problem. That one still has an x in it, and that means it's subject to doing whatever the limit is doing, which is x goes to negative infinity. So I really have to sort of think about what's going on here. So what's happening here is as x goes to negative infinity, 6x also goes to negative infinity. And then what happens when you add 13 to that? Well, 13 is not going to do much to negative infinity. So if I add 13 to something that's going to negative infinity, that still goes to negative infinity. And then if I divide this by 7, that is still going to go to negative infinity. A little bit slower because it's being divided by 7, but it's still going to go to negative infinity. So this is negative infinity. If you took 1315 or a regular college algebra, you would have called this a slant asymptote. And the slant asymptote for this would be y is equal to 6x plus 13 divided by 7. It's the parts that don't go to 0. That's extra. You don't need to know that. Example 12. The profit function for producing and selling x thousands of toothpicks is given by p of x is equal to 5x plus 4 times the square root of x. Determine what happens to the average profit per 1,000 toothpicks as production increases without bound. So let's take a look and see here, what function are we dealing with? We need to create the average profit function. We have profit, but we need average profit. So average profit of x is profit divided by x. So that's going to be 5x plus 4 square roots of x divided by x. And then we want to know what happens to the average profit as production increases without bound. That tells me to let x go toward infinity. So in order to do that, we need a limit. So the limit as x goes to infinity of the average profit function is the limit as x goes to infinity of 5x plus 4 square roots of x divided by x. So here again, we're taking the limit as x goes to infinity, and we have a rational function. So we pick up the largest power term from the denominator, which is just x to the first, and so we're going to divide everything by x. So this is going to give me 5x over x plus 4 square roots of x divided by x all over x divided by x. So this is the limit as x goes to infinity. 5x over x is just 5. Now this one's a little more complicated. 4 square roots of x divided by x. So there's a couple of ways to think about this. 4 square roots of x divided by x. Well, the square root of x is technically x to the 1/2 power. So you can think of it that way. And then you have x to the 1/2 divided by x to the first. So you subtract the exponents. 1 minus a half is a half. And you place that x with the exponent in the location where the larger power came from. So that would be the 1, so it's in the bottom. So it's x to the 1/2 there. And you can leave it like that, or you can rewrite it as 4 times the square root of x. And then x divided by x is 1. And now we take the limit. So the limit as x goes to infinity of 5 is 5. The limit as x goes to infinity of 4 divided by the square root of x is 0. And then the limit as x goes to infinity of 1 is just 1. So it's 5 plus 0 divided by 1, which is 5. And so what that tells us is that average profit approaches $5 per 1,000 toothpicks as production increases without bound. Let's take a look at infinite limits. So, if f of x is a function that increases without bound as x approaches c, then the limit as x approaches c of f of x is equal to infinity. And if f of x decreases without bound as x approaches c, then the limit as x approaches c of f of x is equal to negative infinity. So again, these limits do not exist technically, but the limit is describing the behavior as the function gets closer and closer to c with the x values. So what this looks like on a graph would be something like this. You would have like a vertical asymptote here at x equals c. That means as you get closer to c, then the function increases without bound on both sides and goes to infinity. And let's suppose that we have another one here. And the function decreases without bound on both sides. Then that one would be the limit as x goes to c of f of x is equal to negative infinity. And then the third scenario is, suppose you have a vertical asymptote, and let's just say on the left side it decreases without bound. On the right side, it's increasing without bound toward x equals c. And so that is neither. So that does not exist, period. So in that case, you have different behaviors on either side of c. So we just say it does not exist. Now here's a helpful little diagram to help you remember how to do these problems. So if the denominator still evaluates to 0 after you try simplifying it, then you examine the signs of the function on the left and the right sides of the target number c, and if they are the same sign, and the same sign that's positive, then that means that the limit is going to positive infinity. If they're the same sign on both sides and negative, then that means the limit is going to negative infinity. And if they're different signs, one positive and one negative, then the limit does not exist. Now, we need to be a little bit careful here. It says, examine the signs of the function on the left and right. So you have to be close to the target, and that's kind of vague on purpose. The trick here is you want to get close to the target, but you can't use any numbers that are so far away that the behavior of the graph has changed. In particular, you can't cross any other 0 in the denominator or any other root from the numerator. Example number 13. Find the limit as x goes to 3 of 1 over x minus 3. So x equals 3 is where there's a 0 in the denominator. So now we want to look at the left side. So basically, we're looking for the limit as x goes to 3 on the left of 1 over x minus 3. So to determine this, I'm going to pick a number that is slightly smaller than 3 because I'm on the left side. And I'm going to say 2.9. Then I'm going to test this number in the function. So we're going to get 1 over 2.9 minus 3. That would be 1 over negative 0.1. And actually, I don't even care what the value is. I just care what the sign is. This is a negative value. And that's all you need to know. You could figure out the number, doesn't matter. Now let's look at the right side. The limit as x goes to 3 on the right side of 1 over x minus 3. So to test this, we're going to pick a number that is slightly greater than 3. So I'm going to pick x is equal to 3.1. So this is going to be 1 over 3.1 minus 3, which is 1 over 0.1. That's a positive number divided by another positive number, which is positive. So this left side limit is negative infinity. This right side limit is positive infinity. And therefore, putting those together, the limit as x goes to 3 of 1 over x minus 3 does not exist because they are different infinities. Example number 14. Find the limit as x goes to 3 of 1 over x minus 3 squared. So if we try to evaluate at x equals 3, it doesn't work because we get a 0 in the denominator. So we need to look at the left and right limits. The limit as x goes to 3 from the left of 1 over x minus 3 squared. So I'm going to pick same number as before. X is equal to 2.9. And that gives me 1 over 2.9 minus 3 squared is equal to 1 over negative 0.1 squared. But that's equal to a positive 1, positive number, and anything squared is positive, so that's positive, and that's equal to a positive. So this quantity is positive, so this is going to be equal to positive infinity. And then the limit as x goes to 3 from the right side of 1 over x minus 3 squared. I'm going to pick x is equal to 3.1. It's going to be 1 over 3.1 minus 3 squared, which is 1 over 0.1 squared, which is a positive over a positive again. So this is positive, and this one is positive infinity. And since these are equal, that tells us that the limit as x goes to 3 of 1 over x minus 3 squared is equal to positive infinity. Again, technically the limit does not exist, but we are conveying information about the graph. And I'll even show you real quick what this graph looks like. Here's 3. It's a vertical asymptote, but on both sides it goes to infinity. Right there. Example number 15. Find the limit as x goes to 7 of x squared minus x minus 30 over x squared minus 13x plus 42. So the first thing I would probably do here is see if I can simplify the function. So rewrite the original function, and then let's factor. And we have x and x. What two numbers multiply to give you 30 and subtract to give you 1? That would be 6 and 5. And the 6 has to be negative, the 5 has to be positive. And what two numbers multiply to give you 42 and add to give you 13? That would be 6 and 7. The 6 is negative, the 7 is negative because they're both the same sign. And here you can see that I have x minus 6 as a factor in the top and bottom, and they can cancel. And it doesn't quite help my situation with this limit going to 7, but it does reduce some of the work. The factor of x minus 6 in both the top and the bottom is not going to change any of the signs that I would get if I just simply ignored them, because they would both cancel their signs with each other. If they were positive or negative, it doesn't matter. So I'm going to use this reduced limit to figure out what else is going on. So notice here we still have a 0 in the denominator. If you tried to evaluate it, you would get 0. So we know it's going to be undefined. It's going to be does not exist, and so we just need to figure out if it's going to be an infinity, a negative infinity, or does not exist. So we do the testing. And so let's look at the left limit. The limit as x goes to 7 of x plus 5 over x minus 7. Let's pick x is equal to 6.9. So we can do 6.9 plus 5 over 6.9 minus 7. That's a positive number divided by a negative number, which is negative. So this would be negative infinity. And now let's check the right limit. So I'm going to pick x is equal to 7.1. So 7.1 plus 5 over 7.1 minus 7 is positive over a positive, which is positive. So this is equal to positive infinity. Well, since they are different infinities, therefore we get the limit as x goes to 7, x squared minus x minus 30 over x squared minus 13x plus 42 does not exist. The final topic in this section is continuity. Continuity from a very elementary standpoint is the ability for you to graph a function from left to right without ever picking up your pen or pencil. If you can do that, then we say that the function is continuous. It's like it's connected and it's all the way through and there's no problems. But if you have to pick up your pencil for some reason, say to jump over a hole or jump over a vertical asymptote or whatnot, then the function is discontinuous at that particular point. Now, in a calculus class, we use 3 criteria to determine if a function is continuous. And they are the following. A function f is continuous at x equals c if, number 1, f of c is defined. So in other words, you can evaluate the function at a single point where x is equal to c and come up with an answer. Number 2, the limit as x approaches c of f of x exists. So you got to have a limit that works, which implies that both the left and the right side works and is the same. And then part 3, the limit as x approaches c of f of x is equal to f of c. And this is sort of the biggie one right here. This is it. Because if you can get number 3 to work, then that shows that the other 2 had to work as well. Number 3 says, I was able to get a value for the limit, I was able to get a value for f of c, and those values happen to be the same. Now, if any one of these criteria fail, then you're immediately done and you claim that the function is not continuous, it is discontinuous at that point for that reason. Example 16. Determine if f is continuous at x equals 3 for each of these functions. So what you want to do is you want to go through the criteria and see if the criteria are met so that you can declare that this function is continuous. So the first graph on the left, we look where x is equal to 3 and we look for the solid dot. But there is no solid dot. So we say that f is not continuous. The abbreviation for continuous is CTS at x equals 3 because f of 3 is undefined. And that's a violation of our first criteria. And that's it. You don't have to look any further because we know that it can't be continuous if it failed the first one. Let's look at the middle graph and determine if the function is continuous at 3. So the first thing I want to look at is see if f of 3 is defined. And there it is. We have a solid dot at 3, 2. So f of 3 is defined. So that works. Next, let's look at the limit. So the limit on the left is 2. The limit on the right is 4. So that means the limit as x goes to 3 of f of x does not exist. And so that's the kicker right there. So we would say that f is not continuous because at x equals 3 because the limit as x goes to 3 of f of x does not exist. And that's it. Now another way to think about limits is when you see a big gap between your two functions, then that's how you know that the limit doesn't exist. Finally, let's look at the graph on the right. So we want to check to see if it's continuous at x equals 3. So let's check for f of 3. And yes, there's a solid dot. Now I should mention that the fact that there's a big solid dot right there, I just sort of threw that in for emphasis. Everywhere there's graph is indicated by dots, right? They're all dots. They're just not drawn out as prominently as this one. So, you know, that's a little bit extra. So you're not going to always see the dot there, right? Any other place on this graph would have the dot as well. Secondly, how about the limit? Well, if I come in from the left, I get 2. If I come in from the right, I get 2. And so the limit as x goes to 3 of f of x, that's equal to 2. Let's go ahead and mention that the function value was 2 as well. And now that these two are the same, that means f is continuous. And so f is continuous at x equals 3 since the limit as x goes to 3 of f of x is equal to 2, which is also equal to f of 3. So this one little statement right here embodies all three of those parts. It implies that the function value exists at x equals 3. It implies that the limit exists when x is equal to 3, and it implies that they're both the same. And that is a continuous function. One note here, a function is continuous at every point inside its domain except the points where it fails the above criteria. So as long as it doesn't fail any of the criteria, then it's continuous at all those points, and now we can get intervals where the whole thing is a continuous. Example 17. Determine where f of x is equal to x minus 3 over x plus 5 is a continuous function. So a function is continuous everywhere it is defined as long as it passes those other criteria. Well, here's good news. This is a rational function. A rational function is continuous everywhere that its denominator is not equal to 0. So I'm going to set the denominator equal to 0. We get -5. And then we know that the function is continuous every place else. So f is continuous on -infinity to -5, open, -5 to infinity. So we use the open parenthesis to show that the interval where the function is continuous goes up to -5, but it does not include -5. Example 18. Determine where the piecewise function f of x is equal to x squared minus 1 if x is less than or equal to -2, and 5x plus 13 if x is greater than -2 is continuous. All right, so if I analyze this, we have polynomials. Polynomials are where you have x squareds, x cubes, x to the fourth, things like this, but no fractions where you have x's in the denominator, no square roots with x's under there, anything like that. Just straight across, integer powers, positive integer powers, right? And the rule is that polynomials are continuous everywhere. So polynomials are continuous everywhere. Everywhere. So what that means for us here is that we know that for all of the x's that are less than -2, the function is continuous because it's x squared minus 1. And for all the x's where x is greater than -2, it's 5x plus 13, so that's continuous everywhere. The only real question is f continuous at x equals -2? And that's what we're going to have to decide. So we're going to use the criteria to do that. So the first thing is we need to know what f of -2 is. Well, for a piecewise function, I plug in -2 into the piece of the function where x is allowed to be equal to -2. That's the top part in this case. So we're going to get -2 squared minus 1 is equal to 3. And that's the function value at -2. And then secondly, I want the limit as x goes to -2 of f of x. Because we have a piecewise function, we need to use the one-sided limits to determine the limit value itself. So part A is going to be the limit as x approaches -2 from the left of f of x and that is the limit as x approaches -2 from the left. Now, which of these pieces is on the left side of -2? It's the top piece. So notice how I had to use f of x in this first part right here. That's because I didn't know which expression to use. And so now I know which expression to use, so I can use the correct one. And now I plug this in, so it's -2 squared minus 1. There's no real extra consideration for this being a left limit because I'm dealing with a polynomial. It's all going to work out just fine there. And then B, the limit as x goes to -2 from the right of f of x. And which piece of the function is on the right side of -2? It's the bottom one. So it's 5x plus 13. And again, we can just plug this one in. Oops, where's my plus sign here? Yeah, the right side limit. So it's 5 times negative 2 plus 13. And that is also 3. Oh, well, that's great news. That's great news. So that means, since these are both equal, then that means that the limit as x approaches negative 2 of f of x is equal to 3. That means this is equal to that. The limit is equal to the function value. And that means f is continuous at negative 2. But I've already decided that f was continuous every place else as well. So the ultimate realization here is that f is continuous on negative infinity to infinity. It's continuous everywhere. Example number 19. Find the value of k so that the piecewise function f of x is equal to kx plus 1 if x is less than 4, and x squared minus 7x if x is greater than or equal to 4 is continuous for all values of x. So there's going to be a value for k that will make this continuous, and any other value of k is going to make it discontinuous. So we got to figure out what that value is. So the first thing I would want to know is the limit. Let's look for the limit as x approaches 4. So again, it's one of these situations where we have polynomials before 4, polynomial after 4. So the only real concern is at 4. So let's figure out what that limit is. So in order to figure out what this is, I need to find the left limit. And so that's going to be the limit as x goes to 4 from the left of kx plus 1. Now k is a constant in this case. The x is the variable. So we're going to plug in 4 for the x, and then we get a plus 1 here. So that's 4k plus 1. That's perfectly fine. And then b is going to be the limit as x approaches 4 from the right of f of x. And the right side function is the one on the bottom, so it's x squared minus 7x. And we just plug in the 4 there, so it's 4 squared minus 7 times 4. And that would be negative 12. Now, how does that help me? I have the left limit is equal to 4k plus 1, and the right limit is equal to negative 12. Now, what do I really want? Well, I need the limit to exist. And that's this limit right here. I need this one to exist. But in order to get that to exist, I need these two things to be equal. And whatever value of k does that is going to provide me with the limit, which is going to provide me with a function that's continuous. So we set these equal and solve for k. So we're going to move the 1 over. We get negative 13. So k is equal to negative 13 over 4. And that's the value. So this is negative 12. And negative 13 over 4 is the value of k. That makes the left limit equal to negative 12 as well. We know that that's the function value as well because it's a polynomial with this bottom function. So everything is going to work out there. All right. Thanks for watching.